The topic which we are going to discuss today, the shear force diagrams and the bending moment diagrams, is perhaps the most important topic that you will have in your career as a structural engineer. Later, when you take some of the advanced courses, for example, structural mechanics or structural analysis or advanced structural analysis, you will see the concept of the shear force diagrams and the bending moment diagrams popping at different places. In fact, the room where you're sitting right now, the building where you're sitting, the bridges that you marvel at, the mega structures, the documentaries on mega structures that you see, the construction and the safe operation of each of these structures, of each of these elements, are governed by the shear force diagrams and the bending moment diagrams. So and if you think about it, that these shear force diagrams and bending moment diagrams are actually a part of the internal force diagrams, which means that when you are given a structure, as you see in the figure over here, you have a weightlifter. When you are given a structure and the rod and the weights at the very end and the weightlifter's hands, right, it can be idealized as a beam. You have a beam where you have the loads at the ends, you have the support conditions where with the weightlifter's hands which are there. Given that you have a structure which is subjected to these different kinds of loads, right, how do these internal forces vary, right? How does this internal shear force vary? And I'm using the term force loosely here. Force can mean a shear force or, in a sense, the bending moment as well, right? So how do these elements vary depending upon the structure and depending on the load? So that is what we are going to focus on in this particular topic, right? Now, if you think about it, if you think about the name of the topic that you see over here, that is this internal force diagram, you are not unfamiliar with it. In fact, you have already been exposed to this when we were talking about the axial loading, or even in the torsional loading, if you want to draw how the the torsional forces, how the torque, right, or how the stresses vary across the length of the member, then you're also dealing with these internal forces. So let's maybe just go back and revisit something which we have already seen, not related to the shear force, not related to the bending moment, but something along the lines of the internal forces. Now, you would probably remember this figure over here, that what we had discussed when we were talking about the non-uniform axial loaded members. Now, for the non-uniform axial loaded members, we had a bar over here where we had the forces of the different magnitudes acting at different points of discontinuities along the length of the bar. The bar as a whole was in equilibrium because the forces on the right and the forces on the left, they cancel out each other. But while solving this problem, while calculating the overall delta or whatever you want to calculate, remember that we had looked at each of these individual segments between the points of discontinuities of the force. We had gone and drawn the corresponding internal force diagrams, right? So for example, over here, what we had done, that suppose if I take a section and if I call this section 1, if I take a section here, if I call this section 2, and so on, and I can take one more section over here and call this 3, right? Now, for the section 1, if you remember that when we had drawn the free body diagram, right? So this is the part, this is my section 1. Here I have a force of 5 kilonewton, right? So I am going to have an internal force over here in 1 as 5 kilonewton, right? So if I go ahead and draw the internal force in this segment from A to B, it is a tensile force, and for these internal axial loads, what we are saying, tensile is positive and compressive is negative. It's a type of convention. We had gone and drawn this 5 kilonewton over here. Similarly, if you take another segment number 2 over here, and if you draw another free body diagram from this left hand corner A all the way to the 2, you will find that the internal force comes out as a -3. We have done this in the chapter on the axially loaded members. So essentially what we get at the end of the day is this axial force diagram. This is also a diagram of the internal forces. Remember, this N that you see over here, this N was nothing but internal axial force, right? So we have already gotten a glimpse of how the internal forces vary. Now, This is a bar which is under pure axial loading. Although it's a non-uniform, there are no loads which are acting perpendicular to the longitudinal axis of the bar. So in an essence, it is not functioning as a beam. Right? Now let me go ahead and present to you a beam over here. Right? So this beam, as you see, it's a cantilever beam. It is clamped at this particular end. Now for this beam, if I apply a load, maybe a load about this particular direction, say I'm going to call the load F over here. Now what kind of internal forces and internal stresses does this load impose? Now for this F, I can split into two components, one vertical component and one horizontal component. So let me go ahead and draw them as well. Suppose this is the vertical component and this is my the horizontal component that I have, and let me go ahead and put names to them as well. Suppose this is my P and this is my Q over here. Right? Now remember the principle of superposition. Now this beam, this force F, now I split into P and Q. Right? Now if I have to go and apply the principle of superposition and take this beam and draw as these two different beams that we have over here, then in the first beam suppose I am just going to apply the force Q that is acting, and in the other one I am going to go and apply the force P. Both of these together essentially gives me my original loading over here. Now this is the case which we have already seen. We have seen that when you have a bar and you're pushing with a force P, how the internal forces and how the internal stresses vary. Right? So this is something which we have already done. Now the question is that for the right hand side beam, for this particular beam that you see over here, there are two questions. The first question is that what are the internal forces, right? And the second question is that how do they vary? We have not dealt with this case before. So for this load P which is acting over here, I don't know how the internal forces vary along the length of the beam, right? And how do they vary over here, right? So this is the intro that will lead us to the path of drawing the shear force and the bending moment diagram. So since we have already looked at this particular case over here and we are investigating what kind of the internal forces does this impose, let's go ahead and solely focus on beams where the loading is pretty much more or less almost always which is perpendicular to the longitudinal axis of the beam, right? So let's go ahead and look a little bit more deeper into this kind of beam structure that we have over here. Now I'm going to present to you the same beam that is there. This particular beam, A to B, as we saw before, and a load at the end, which is P, a vertically applied load. Right? Now, similar to what we had done for the axial loading case, I am going to go and here I am cutting a section MN. So this is my section MN over here where I've cut a section, right? And I am going to do the exact same thing. I have a left side and a right side right now. So let me go ahead and mark that. So this is my left side and this is my right side over here, and I have separated and taken my left side over here, right? And this is my right side. Now similar to what we had did, now again all I have to do is to sort of figure out what are the internal forces which are acting just to keep these individual chunks in equilibrium. So when I am looking at my left chunk over here, at this interface, right, I can have three kinds of forces. I can have a shear force, like a force which is acting vertically down or up, right? I can have a moment, I can have an axial load as well. In this case, I'm not going to have any axial load because there is no force along the particular x direction that is there, right? If you are considering, say, this is your x direction, so there is no force in the x direction, there is not going to be an axial force. So at that interface Mn, the forces I'm going to have are something like this. I'm going to have a force V and I am going to have a moment M over here, right? Now, since this section Mn is the same over here and the same over here, so let me go ahead and further elaborate. This is the section Mn and this is the section Mn over here. When I'm looking at the right hand side, I must have equal and opposite force V and an equal and opposite M acting over there, because that point is not going anywhere. That point is in equilibrium. So here also I will have vertically up V and clockwise moment M. Now, going from the perspective of pure establishing equilibrium, what do we get? So from this particular portion, the left hand side, if I have to draw my V, if I am doing my summation of Fy equals to 0, this one gives me my V as equals to P. So my shear force that is acting, V is the shear force, right? So maybe I write it more explicitly. So this V over here is shear force, right? And this M is bending moment. So my V is equal to P over here, right? And how do I find the moment? So if I take the moment of all the forces about this particular section, Mn over here, what can I write? That I am just doing the moment equilibrium, that my summation of moments must be equals to 0. That gives me P times X, because I have taken this section Mn at a distance X from the left, right? Will be equal to, so P times X is a clockwise moment, right? Plus V times 0, because I am taking the moment exactly at this particular section, minus M. It depends upon what you are taking as a positive or a negative. So this is the overall equilibrium equation, is equals to 0. So this essentially gives me that your bending moment at that particular point is P times X, right? So now try to appreciate that what we just wrote over here. Here, for this structure, for this cantilever, when I'm having a load P at the left end, it does not matter where my X is, my shear force at anywhere where I take is going to be equal to P, because V is only dependent on P, it does not depend on X, right? Whereas your moment over here, the bending moment at any section, depends upon the load P and also depends at the distance where you are taking that particular section. So it is P times X over here, right? So this is a case where your shear does not vary as you are going from the left to the right? Shear stays constant, and we will see this again when we draw the bending moment, when we draw the shear force diagram. And the moment is a function of X, right? So the moment keeps on varying. The moment is 0 over here, it's a free end. The moment is 0 at this particular free end at X equals to 0. And as you keep on moving, the moment becomes a product of the load times the X over here. Now, will this be true for all kinds of loading cases, for all kinds of structures? Of course not. It is going to depend upon the nature of the loading. It is going to depend upon the type of the structure that we have. For example, if I give you this generalized structures, these generalized beams, right? Maybe the left one is simply supported, as you can see. It has different kinds of loadings. It has a vertically applied load, it has an inclined load, right? The one on the right, it also has an inclined cantilever beam. It has a trapezoidal load that is there. So for these kinds of configurations that we have over here, your V as well as M, V is going to vary along the length of the structure. Right, so it's not a constant anymore. Neither is V constant nor is M constant. They're depending upon the loading, depending upon the structure. So maybe we make a general note of it. So V and M varies along the beam, right? So it depends upon the nature of the loading depends upon the type of structure that you have over here, right? So in a nutshell, the variation of the V and the variation of the bending moment M. How do you represent the variation? What we saw in the previous page, that the shear force and the moment varies, but how do we represent that? How do we capture that? The best way to capture that is to draw diagrams which show how from the end A to the end B, end A to the end B, depending upon the loading conditions and the structure, how does this shear force V and how does this bending moment M vary, right? So this is essentially what this next page shows in a nutshell, that the variation, so this is important, the variation of the shear force V and the bending moment M along the structure is represented by the shear force diagram, and this is usually termed as an acronym as SFD, that is the shear force diagram, and for the moment we have a corresponding bending moment diagram. So this is known as BMD. Typically in short form it is used that draw the SFD and the BMD of this beam with this particular loading, right? And why is it important? Why are we doing all this? Why are we trying to break our head and take a beam and have the loads and find how the shear force and the bending moment varies? Well, the critical point that you have to remember is that you design structures such that they don't fail at the points of criticality. At the points within your structure, the room where you're sitting in, the beams and the columns and the slab, right? The points along the beams are subjected to all the different kinds of loading, columns are subject to different kinds of, and the points within these beams and the columns and the slabs, if you draw the shear force diagram along the length of the beam or the bending moment diagram along the length of the beam, you will see that there are points where these values peak, these values become maximum. So if you had to keep on increasing the load, these points become prone to failure. So the shear force diagram and the bending moment diagram, it helps you to find the maximum values of the shear force and the bending moment so that you are designing safe structures. And this is applicable for civil engineering structures, for mechanical engineering structures, for aerospace structures, and it has other wide range of applications, right? So the whole objective of drawing shear force diagrams or seeing how the shear forces vary across the structure, how the bending forces vary across the structure to the bending moment diagram is so that you are designing structures which are safe to resist the loads the structure expects to undergo. Right now, one thing which I want to bring your attention back to, right? We wrote for this cantilever beam, which we just looked at, right, with an end load P, we wrote the shear force V and the bending moment F. Now, what is the convention? Remember, we always have to deal with some conventions so that you and I are talking the same language, right? You are, what's positive to you may be negative to me, right? But we have to have one convention so we understand each other. Now, that's the whole point of having conventions anyway, right? Remember that in axial loading, now again, I'm just talking about conventions. In axial loading, we have also had followed one convention that if the bar is under tension, that's positive. Probably you followed the same convention when you studied trusses in engineering mechanics. If the truss member is in tension, it's positive. If it's in compression, it's negative, right? For the shear force and the bending moment, there are also conventions. For example, if you take a look at this beam over here, you see that this section MN, I could have cut this section going from left to right or from right to left, right? So when I have cut this section from left to right, I have this V pointing downwards M here, and at this point we are going to have a equal and opposite, right? So what is the positive convention for a positive shear and a positive moment? Well, the positive convention for shear is that if the shear force is trying to rotate your element in a clockwise manner, that is called a positive shear. Take a look at this figure. In this figure, this force V over here, if this is your element, this force V tends to rotate the element in a clockwise manner, right? So it tends to rotate the element in a clockwise manner over here. Similar to this one over here. Here, this force V also tends to rotate the element in a clockwise manner, that is there, right? So a positive shear is the one which tends to rotate your element in a clockwise manner. So let's just make a quick note of that. So positive shear is the one which tends to rotate element clockwise, right? And what is a positive moment? Well, the moments we have drawn, which we have drawn here, is also positive, so that probably gives you a hint that what we mean by a positive moment. A positive moment is the one which turns your beam into a trough, or it causes sagging. Which, what I mean by that, if you take a, if you consider this moment M over here, right, what this moment essentially does is that it is essentially making your beam curl downwards. So if this is my, you know, the say the end A, this moment over here is trying to sag, it is causing a sagging of the beam. There are two kinds of phenomena. This is called hogging, over here, and this is called sagging, right? So the moment, the easiest way to remember that is the sagging is the smiley face. So if you have to draw, this is my sagging, right? So sagging means a smiley face. So a smiley face is a positive thing. So that's the best way to remember what is a positive convention for a bending moment, right? So this bending moment over here tries to turn my beam into a trough, or it causes a sagging kind of a phenomena. Similarly, this bending moment over here, the equal and opposite one which is acting, this also tries to convert your beam into a trough. So in this particular, if this is my clamp 10B, this particular case also I'm having a sagging kind of a moment over here. So a positive moment is the one which tends to cause sagging, right? Or converts the beam to a trough, right? I hope that is clear. Now again, just to reinforce that one, if I say take a section, say, of this particular chunk of this cantilever beam over here and look at it a little bit more deeply, this is what I have, right? So this is my positive V, positive M, positive V, positive M. Now don't be confused that this is positive V. It is not related to your positive X and positive Y. It is just related to what is the nature of action of this force. It is not along the positive Y or positive X or something like that. It is the nature of action. Positive V is the one which tries to make your beam rotate in a clockwise manner. So if you see over here, both in this section, this V tends to rotate your element clockwise, even in this section tends to rotate your element clockwise, and this V and this V must be equal and opposite because they're looking at the same section over here. Similarly, the positive moment tends to, for this section, tends to turn your beam into a trough. Even in this one, tends to turn your beam into a trough, or makes a sagging kind of a moment, right? So if I just have to draw an overall positive element, what does that look like? A positive element. So if this is my, say, the element of the beam, right? If I am having to draw the forces, the positive forces on the right hand side over here, right hand side meaning I'm coming from left to right, similar to over here, I'm coming from left to the right portion over here. So here my positive shear will be acting like this. My positive moment will be this. So this is my V, this is my M over here. And if I'm looking at the left hand side, I'm going from right to left, here also from right to left here. So here my positive V is acting vertically up, and a positive moment is acting like this over here. So this overall is a positive element, right? Let's take a look at the forces again. You see this V and this V, how does it tend to rotate the element? It tends to rotate the element in a clockwise manner. And you see this M and this M over here tries to sort of, tries to sort of curl your beam, or cause a kind of a sagging kind of a movement over here, right? Now if I have to maybe separate this V and separate this M, and if I have to write that, essentially what I can represent this as, if I just draw the shear. So sorry, let me erase that. So if I just have the shear, I can draw it simply using an element as well. So this V and this V over here will tend to sort of make your element like this. So this is the positive shear. I am again applying the principle of superposition. That's all I'm doing. And for the same thing, how does the moment look like? The moment will be something like this. The sagging phenomena. Right. So I hope it is clear to you that how do we represent a positive shear and a positive moment, because these conventions become important when you are drawing the bending moment diagram and the shear force diagram. Now next, what we are going to look at, we are going to look at some of the types of beams, right? Then we are going to look at some of the necessary tidbits, some things that you should know as a structural engineer, that what are some of the cases where the bending moment and the shear force turns to be zero. We had seen a case where, you remember, when we had that internal hinge and internal pin which does not support any bending but only the loads in the x and the y direction. And then we are going to look at some problems on drawing the bending moment and shear force diagrams.